Wait, we already finished 4.1?
Huh?
When?
It was like a 4-day thing.
Okay, 4.2, exponential functions. What do y'all remember about exponential functions? Something. Okay, I'm recording these comments like that aren't necessary, sir. What do you remember about exponential functions? Huh? Huh?
Exponents? Like it has
What's the exponent?
X.
The variable. So when you're talking about exponential functions, that puts the variable in the exponent. Okay? Do y'all remember what the graphs of these look like? What they did? What does an exponential function do? What happens when something grows exponentially? Or what happens when you have exponential decay?
It goes down
Extra.
at a higher rate.
At first. Okay. So remember, exponential growth, it's increasing. It's increasing slowly, and then it just takes off. Exponential decay, it's coming down really fast, and it slows down. If I take a candy bar and cut it in half, and then cut it in half again, and cut it in half again, will it ever go away?
No.
No. It gets closer and closer to
0.
0. Okay, that was some stuff about exponential growth decay. Bacteria that grow pretty quickly.
Wait, a candy bar never goes away?
Not if you cut it in half over and over and over. Theoretically, you could always cut it in half and still have it left over.
You have to be able
What do
to
you mean
cut it.
theoretically?
The pieces would be so small, you would not be able to cut it anymore.
Uh-oh.
But if you were able to cut it in half over and over, it would never go away. Bacteria. If you've got a petri dish, it's got some bacteria in it. What's going to happen with that bacteria? It's going to grow, right? Fast. Fruit flies. You have fruit flies in a little jar with a piece of banana. You might have 2 fruit flies, and then you've got 4, and then you've got 8, and then you've got 16, and then you've got 32, and then you've got 64, and it's just taken off. Okay? Exponential growth. Have I ever showed y'all the bread experiment?
Yes. Well, I've seen it, but.
Okay, so the bread experiment works like this, and this is going to give you an idea about bacteria and how it grows and everything. So a teacher took a fresh loaf of bread, and with that fresh loaf of bread, she took a pair of tongs that were sanitized, reaches into the bag, takes out a slice of bread, and puts it into another bag and seals it. I don't remember how long this took. Might have been 5 to 7 days. What does that piece of bread that she took out of that one sack and put it into another sack look like after, say, a week? Has it changed in a week?
No.
So in a week,
Moisture in the bag?
do what?
If the moisture in the bag?
Well, it's a brand new bag. So essentially the bread after a week looks like this. Okay? So this was the control piece. This is an experiment. So in an experiment, you have a control group, right? You have a control group, and then you have the experimental pieces. Experiment number 1. Go to the sink, use soap and water, wash your hands thoroughly, dry them off with a sterile towel. I don't want you to dry off with a dirty towel. I want to make sure the towel is nice and clean. Reach into the bag with your hand, grab a piece of bread, put it in a bag. We're going to put it next to this one for about a week. What's that bread look like?
This is
Well,
rolled
it's gonna
down,
be
like that. But
It's gonna be the same thing.
Okay? So after a week with washed hands, picking out a piece of bread, there you go. Not bad, huh?
I feel like the only reason that it looks different is because you had to actually like grab it and pinch it with your hands.
Possibly. Okay. Okay. Now, what have we been doing with this every period this year? Because what's this do?
Killing bacteria.
Because this is going to kill the coronavirus,
Yes.
right?
Because it's that.
So this is essentially the same thing as getting some hand sanitizer, right? So, the next student is going to use some hand sanitizer. Wash his hands with hand sanitizer, make sure they're dry, reach into the bag, grab a piece of bread, put it in a bag. What's it look like?
Moldy.
Moldy.
But wait a second. This is gonna kill the coronavirus.
No,
This is gonna make sure everybody's safe,
99.9%.
okay? Okay,
Ooh.
there's the piece of bread after the person's hands were cleaned using hand sanitizer, grabbing a piece of bread and putting it into another bag for a week.
It's like the same.
And you kept it in the same spot.
It was just touched that one time. Take it out and put it in the bag. That's it.
For a
That's
week?
all that was done. No, it stayed in the
Once,
bag.
when I moved into the bag.
Yeah, you take it out of the bag of bread and put it into this bag to just sit.
For how long?
About a week,
Oh,
That's nasty.
okay?
that's a week.
Now, another person, hey, before you wash your hands, don't even wash your hands. Just come up, grab a piece of bread and put it in a bag,
And it's clean.
okay? Unwashed hands, what's it gonna look like?
Just
It
shit.
it's moldy.
It'll look like that.
Yeah.
What if it doesn't
It'll,
look
like that
moldy?
small part will be all, yeah.
Unwashed hands.
What if
Guys,
it-
we're talking about exponential growth. We're talking about bacteria. We're talking about stuff. Okay, the last one. I'm going to use some sterile tongs. I'm gonna reach into the bag. I'm gonna grab one piece of bread. I'm gonna take that piece of bread. And I'm going to, with the tongs, rub the piece of bread across this Chromebook. I'm now gonna take that piece of bread and put it in the bag.
The whole thing's gonna be like.
It's
Wow.
completely moldy.
Well, that's not
It's
bread.
just-
That looks like a rocket.
Rat.
Okay? And here it is.
Did you burn it?
Looks like a rat. Wait, did you do this?
Did you know, true story, a public toilet seat
It's
cleaner
cleaner.
is cleaner than a cell phone that you stick to your face every day you make a phone call on,
I don't.
What?
I put my phone on speaker.
I clean mine
Yeah.
every.
okay? Your cell phones are nasty.
I think
Yeah, but
I
not if
might
you clean it with an alcohol wipe.
Okay.
But clearly look at how the like sanitizer works. I
Yeah.
think that's the same concept.
Right?
Yeah.
Those, someone made a fortune by selling those phone sanitizers. Put your phone in this little box, it'll say, shut up. No, it does not. I ain't buying that. Anyway, I'm showing all these because this is, basically say a week's growth. So bacteria, just a little bit of bacteria on something is going to grow exponentially. And some surfaces obviously are cleaner than others. So we're talking about exponential growth, exponential functions in this section. So here is the definition of an exponent and the properties of an exponent. And I'm gonna rewrite this. That's the same thing as saying a to the m over n, right? And we've done this before. When you have some number raised to a fractional power, the denominator goes there. What is that called?
The power, like the.
What is that n called?
Square root exponent.
No. Shoot. Give me the first letter.
I,
Oh shoot! Yeah, no, never mind. I was thinking of a K.
What's the second letter?
n.
Integer.
Integer?
How is that a word?
Wait, let's say it.
What's the third?
The
Index.
index.
Okay.
Okay.
I was
So when you raise a number to a fractional power, the bottom number is the index. The index is the number that's inside the little radical thing. And if there's not a number there, it's assumed to be what?
2.
Yeah, there's a 2 right there, but I don't write it because it's assumed to be 2. That's which is why we call it a square root, right? If I want the third root,
I like that.
I thought it was
Okay.
an arrow.
Cool.
What happened?
so apparently I was trying to draw Van Halen or something. I don't know.
No.
Oh, you should have kept it.
Okay, so if there's a number there that you want to be there, otherwise it's gonna be a square root. So that's the square root of 4, and below the square root of 4, that is the cube root of 8. And the top number in a fractional exponent, the top number is the power. And you can put the power outside the parentheses, or you can put the power inside the radical. It doesn't really matter. Okay? Those mean the exact same thing. Moving on. Here are some of the properties for exponents. We're talking when a is greater than 0, but not 1. Because if you raise 1 to a power, what do you get? 1 to the 12th power is
12.
1 to the 12th power is 1. 1 to the half power is 1. 1 to the 3/5 power is 1. 1 to the millionth power is 1. So a has to be greater than 0, but not 1. A to the x power is a unique real number for all real numbers x. The domain of an exponential function is all real numbers. The domain of an exponential function, all real numbers. Negative infinity to infinity, that's the domain. If I have a to the b power and a to the c power and say that they're equal, that can only be true if b and c are equal. Exponential functions are either always increasing or always decreasing. And because they're functions that are always increasing or always decreasing, that makes them 1 to 1. So, do exponential functions have inverses?
Yes.
Yes. And they're called natural logarithms or logarithms, which that's coming up.
As in this lesson, or?
No.
Oh.
If a is greater than 1, say 2, and m is less than n, so a to the m is less than a to the n, well, is 2 to the third less than 2 to the fourth? 2 to the third is 8, 2 to the fourth is 16. 8 is less than 16, right? So if a is greater than 1, then you can look at the exponents and see which one's bigger. But if a is between 0 and 1, it's the opposite. 1/2 squared is 1/4. 1/2 cubed is 1/8. 1/4 is bigger than 1/8. Okay, so that's just some properties of exponents. Next slide. This is an exponential function with base a. We're going to calculate the values of each of these 4 items. F of -1 means take the function f of x is equal to 2 to the x power and write that as 2 to the -1 power. What do we do with negative exponents?
Oh, we put them on the bottom, right? No, I don't know.
We change position. If they're on the top, we move them to the bottom. If they're on the bottom, we move them to the top. So remember that I can write pretty much any number as a fraction. So if I wanted to get rid of this -1 exponent, all I have to do is take that 2 to the -1 and pass it through the fraction bar. As soon as I pass it through the fraction bar, the exponent sign changes. So it would become 1 over 2 to the first power. So passing it through the fraction bar, the exponent sign changed. And of course, 2 to the first power is just 2, so the answer is 1/2. F of 3, well, that's 2 to the third power. And 2 to the third power is 8. Part C, we have f of 5/2. Well, that means 2 to the 5/2 power. What's the 2?
2 is the index.
Okay, so that's the index. So I need a square root, but I'm not gonna write the 2 inside the radical because it's obvious that it's assumed to be a 2 if there's no number there. Where's the 5 go?
Outside.
And the square root.
It could go outside if you want to put it in parentheses. I'm gonna go ahead and put it on the inside, 2 to the 5th power. And what is 2 to the 5th power?
10. No. 10. I don't know.
2 times 5 is 10, but I'm not asking that question. The question I'm asking is 2 to the 5th power.
64.
No, that's 2 to the 6th.
32.
32.
Okay.
And does that simplify?
Uh,
Okay, do y'all know how to do these in the calculator? Simplify radicals in the calculator? Okay, let's do this real quick. Remember when you're trying to simplify radicals, in this case square root, I am looking for perfect squares that go into, in this case, 32. Where's my calculator? I clicked on it and it hasn't popped up yet. Okay. Okay, if you go to y equals, the problem we're doing right now is I want to know the biggest perfect square that goes into 32. So I'm going to take 32 and divide it by a perfect square. That would be x squared. Y'all good with that? If I was looking for what's the biggest cube root that goes into 32, I would take 32 divided by x cubed. It doesn't matter what it is. If you're simplifying a radical, it's going to be the number that you're simplifying divided by x to the index power. Okay? Go to the table. What I'm looking for here are nice numbers. Let me read these to you. 0 doesn't work. Okay. This is 1 times the square root of 32. Well, I'm pretty sure that 1 times the square root of 32 is the same thing as the square root of 32. This is 2 times the square root of 8. This is 4 times the square root of 2. And there's none other below that. So to simplify the square root of 32, the biggest number here, smallest number here, or the biggest number here is going to be 4 root 2.
So that's the answer.
Yes. So the square root of 32 is 4 square roots of 2. Sorry.
Is it the baby?
I don't know. No, nothing. No message.
Maybe. Yeah. Just having another granddaughter?
Yeah.
Have you looked up?
Yeah.
Why did you say that question like?
I don't know, because I said congrats to somebody else and they're like, it's not really that great. And I was like,
Okay.
I don't know.
So what has nothing to do with these. I'm going to do it in a different color quick. I want you to simplify this for me. Square root of 512.
Oh my gosh. Okay, wait, I'm gonna buy you this.
Do the square root of 512 for me. Simplify it.
Forgot to do 2 after.
8 times the square root of 8. That's my final answer.
No.
Wait.
Gosh.
Because the square root of 8 has a perfect square still in it.
Wait, okay. No, nobody answered.
16 times the square root of 2.
16 root 2.
I'm so confused. Oh. I typed it,
No, you
Okay,
but it didn't work.
so I'll do it.
calculator square.
Clear this. 512
That's cool.
divided by x squared. Go to the table. I want to go down as far as I can. Well, there's 8 root 8, but I'm still at 6 over here. There might be some more. So keep going down. Oh, that one looks good. Anything else going to happen? No, it's not going to happen. 16 root 2. That's how you simplify those the easiest way. Okay? Part D. F of 4.92. Well, that's going to be 2 raised to the 4.92 power. And how do you do that?
Yeah.
Yes, you just type it in the calculator.
Say 4.92.
It's 30.27.
30, but what?
0.27.
Okay.
Or do you want all the numbers or just?
Just pay, when you're answering a question, pay attention to what it says to round to.
Oh, okay.
Okay? I didn't specify anything, so I'm good with that. Questions so far, guys? Okay. Couple more pages of notes.
Wait, is this it?
No. Okay. So I have an exponential function here, a to the x power. I'm going to let a be 2. What is the domain of all exponential functions?
All real numbers.
All real numbers, which is negative infinity to infinity. Okay? What is the range?
0 to
Can it be 0?
no.
Right? It'll never be 0. That's why it's parentheses. Don't give me a bracket.
Is it an asymptote?
Okay?
It'll never be a bracket.
The x-axis is an asymptote.
Oh,
Okay? For the parent. Now, guys, we're going to be doing all kinds of transformations of this. Reflections, moving it up and down, left and right. But we're talking about basically the parent exponential function where a is greater than 1. When a is greater than 1, look at the graph. It's going up. It's always increasing. Because it's always increasing, that's why it's 1 to 1. That's why there's an inverse. Notice these 3 points. -1, 1 over a, 0, 1, and 1a. Those points are going to be on every graph. So in the case of the graph of 2 to the x power, -1, 1 over 2, 0, 1, and 1, 2. So this is an example when a is greater than 1. What about when a is between 0 and 1? When a is between 0 and 1, what's it going to look like? Is it going to be growing? What happens if you multiply something by a number less than 1?
it gets small.
It gets smaller, right? If you take a half of something, and then a half of that, 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 right? So here's the example for that, maybe. Okay. This graph is always decreasing. It's continuous on the entire domain. The domain is still negative infinity to infinity, or all real numbers. The range, 0 to infinity. The x-axis is the horizontal asymptote. Notice those 3 points. -1, 1 over a, 0, 1, and 1 over and 1a are all points on the graph.
Wait, so only whenever it's smaller than 1 is it decreasing?
Between 0 and 1.
Or, okay.
Between 0 and 1. Okay. Here are 6 graphs, all graphed together.
Wait, it's like a firework.
Huh?
It's like a firework.
Like a firework. Do all 6 of those graphs have a point in common? All 6 of those graphs go through the point
0, 1.
0, 1.
What?
Wait, why isn't it?
It's counting by halves. Pay attention.
Oh, I see.
Okay. All 6 of those graphs go through the point 0, 1. Notice that the further you get away from 1, the steeper the graph is. So if we're talking about values between 0 and 1, 1/10 is further away from 1 than 1/2 is, right? So 1/10 is steeper than 1/2. Over here, 10 is further away from 1 than 2. So it's steeper, okay?
No.
Not in here today.
Yeah.
I'll come over here and rattle your desk some.
Yeah, I don't. I'm just like,
I know.
I know, it's
I
like
looked at
keep
you and all,
walking over
I
here.
looked at you and all I saw was the white of your eyes because the color of your eyes just rolled back into your head.
If you go on the thing, you'll see her like camera turn on and off, and you'll just see her falling asleep in front of the camera. I don't know why.
Oh, this better be a good.
Is it-
message.
No, it's not a text message. Dang it.
We get so excited.
Update from my Robinhood account.
What is that? You steal from the rich and give to the poor?
Absolutely.
Eat the rich.
All right, characteristics of the graphs. We noticed as we looked at both values of a from 0 to 1 as well as greater than 1, that the points -1, 1 over a, 0, 1, and 1a were all on the same graphs. When a was greater than 1, it was increasing. When it was between 0 and 1, it was decreasing. All right, so nothing new there, yes? Okay. We're going to graph 1/5 to the x power. Will this graph be increasing or decreasing?
It will be decrease.
I heard both answers. Somebody's right. Decreasing, why?
Because it's less
I read the
than
number
1.
backwards.
Between 0 and 1. Okay? So, plug 0 in. 1/5 to the 0 power.
What's that?
1/5 to the 0 power.
Zero.
1.
Error.
Anything raised to the 0 power.
1.
Itself.
Every graph includes the
1/5.
point 0, 1. Okay, good. 1.
Oh.
You love statistics.
Okay? So, we saw 6 graphs all went through the point 0, 1, didn't we?
Oh, yeah.
What?
For sure.
Wowzers.
It's Wednesday.
Plug in 1.
Hump day.
1/5 to the first power. Are you using your calculator to do 1/5 to the
It's
first
1.
power?
It's 1. 1 to be 1?
It's 1/5.
One
One
fifth.
fifth.
It's 1/5.
You're
1/5.
so close, but so far.
So 1, we're at 1/5.
I feel like we're gonna give you a
I'm
headache.
so glad this is recording.
I'm not.
What is 1/5 squared? Don't use a calculator.
2/5.
1/25.
1/25. Okay, are we gonna have a problem graphing?
No.
Yes.
Yeah.
Probably. You see what's happening here?
Yes.
I mean, this thing is getting smaller and smaller, but we know that it's not gonna cross
It's
the
never
x-axis.
gonna cross.
Let's go the other way, -1.
Yay.
1/5 to the -1 power. -1 power simply means
1
Take
and
the reciprocal.
1/5. So 5.
so 5.
1 and 1/5. Is that what you said?
-1, 5.
You have a 1 in 5 chance of getting it right.
-2 power. The negative means take the reciprocal.
So it'll be 25. Right?
So we have 5 squared, which is, okay, I can't graph that. So it's gonna come down here. It's getting flat, getting closer and closer and closer to the x-axis. Up here, it's taken off. And that is the graph of f of x equals 1/5 to the x power.
So it's always gonna go through
Okay.
1.
Are we done?
Or the 1.
Okay, I'm gonna go ahead and stop there.
So the y-intercept is always gonna be 1.
0, 1. As long as there's no reflections or translations or anything like that taking place,
think you just want
which we'll get to those tomorrow.
So if it's just
Summer, you're good to go,
a
kiddo.
to the power of x, it's always gonna be
Have a good day.
0, 1.
I thought you were like